Large language models are notoriously opaque, making it difficult to trust their underlying reasoning. When a model processes a prompt, it generates internal activations, complex numerical vectors that represent its internal state. But because these raw numbers are unintelligible to humans, we need a way to translate these thoughts into something we can actually audit: natural language. Mathematically, these activations are just points in a high-dimensional vector space. To decode this geometry, we need a bridge that maps these abstract numbers back into human concepts. This is where the autoencoder comes in. Traditionally, these models compress data through a narrow bottleneck to find a simplified representation. If we can reconstruct the original activation from this bottleneck, we prove it captured the core intent. A natural language autoencoder, or NLA, takes this further by forcing that bottleneck to be human words. This forces the model's inner state into a readable format we can finally audit. The NLA uses two modules: an activation verbalizer to compress the data into text, and an activation reconstructor to map that text back into the original mathematical space. Success is measured by how well those thoughts survive the round trip. We quantify this success using the fraction of variance explained, or FVE. A higher FVE score means our text explanation accurately mirrors the model's internal logic, turning opaque computation into a verifiable window. To reach high fidelity, we move beyond simple supervised learning. Using reinforcement learning, we reward the NLA when its text descriptions lead to more accurate reconstructions, giving the explanations true causal power. As these reconstruction scores climb, the NLA becomes increasingly informative across specialized tasks. This allows us to scale our oversight, auditing the model's internal goals using the very language of human values. For example, it can reveal a model's hidden intent, such as planning a rhyme. This proves that specific strategies exist internally well before the final words ever appear on the screen. We can verify this is causal through steering. By editing the text label, the reconstructor generates a new vector delta that physically shifts the model's state, forcing a predictable change in its behavior. This steering also exposes why models fail. We can see internal salience rising as a model fixates on a specific language or bias early on, causing it to ignore later instructions. These insights act as debugging tools. By tracing a fixation back through the internal state, we can identify root causes, like malformed training pairs that corrupted the model's pattern matching. However, NLAs are not foolproof and can sometimes confabulate details. They are highly accurate at identifying broad themes, but we must remain skeptical of their granular claims about specific entities. To filter out these hallucinations, we look for recurrence. Genuine concepts persist consistently across sequential tokens, while errors appear as transient flickers. Frequency of presence becomes our primary trust heuristic. We further validate these findings by flipping detected concepts. If changing an even number reward to a penalty shifts the output as expected, we've confirmed the NLA identified a real decision criterion. This is vital for detecting situational awareness. A model might hide its intent to pass a safety test, but the NLA can expose this deception by reading the thought behind the neutral speech. Consistency across deployment and evaluation scenarios confirms these aren't just guesses. The NLA acts as a causal mirror of the model's true internal awareness. This makes NLAs a game changer for external auditors. Without needing access to training data, they can decode complex reward biases into human-readable text to ensure models align with human interests. Despite this power, we must remember that language has limits. These labels are our best linguistic approximations, and the high cost of implementation means we must use them strategically. By bridging the gap between vector math and reasoning, NLAs let us read what models think. We just have to remain rigorous, using recurrence and steering to verify every word.